Hello everyone. So I am now delivering the fourth lecture series of the seismic, that is single channel shallow seismic instruments and the data acquisition by Geological Survey of India with the coastal vessels. So in these lectures, I will be delivering about the case study example, means practical seismic section, how we will acquire in the field, and I will be of course delivering about it in a marine domain, in the marine aspect where I am working. So in my previous lectures, I have already talked about the basic seismic principles and how the data is being acquired, what is the noise elimination technique. Still in this lecture, I will be talking about some theory, that is the acoustic rays being emitted from the source. It is getting reflected from the subsurface layer, and reception is being done by the the receivers, and then data acquisition is being carried out by some software, and then digitization followed by, and at the last we get to the seismic images. So steps by steps I'll be talking about all this. So let's go through my this lecture. Hope you will find it beneficial for your future use. So these are the coastal research vessels of the GSI. One is RV Samudra Kaustubh, that is carrying out survey in the east coast of India, and another is the Samudra Saudhigama, that is carrying out research in the west coast of India. But these are look alike, same, and the length is same, dimension is same. These are like twin ships, the daughter ships. What are the shallow seismic components used by these coastal vessels? One is obviously position system of navigation, that is GPS. Second is the power source unit. Third is the electrodes of the sparker. Four is the streamer. That is consist of single channel with some number of hydrophones. And fifth is the data acquisition unit, that is the delve seismic. The basic principle is to emit this acoustic wave. The wave travels through the sea bottom and the subsurface layer, and will record the acoustic signals that is being reflected by the geological layer interfaces. So we have a seismic source, we have a receiver. The principle of imaging is to estimate from the recorded seismic trace the true geophysical profiles, and we will have the two-way travel time to depth and retrieve the physical parameters. That is, there is density, there is absorption, there is a propagation velocity, there is acoustic impedance. So this is the mainly shift. There is also echo sounding system is there, from which we can measure the water depth. But our objective is to have the seismic section. So we are having sparker is being deployed and the sound source, and there is a streamer hydrophone assembly. So we'll discuss about this. So generally ray is getting reflected from the subsurface layer by the sparker, emitted by the sparker, and it is being received at the hydrophone assembly, and we'll get the subsurface layer information. So first we'll talk about the power source unit. Generally, this is the power source unit what we will use in GSI Marine for shallow survey, that is the 6J2 Mille. It is imported from the France. So generally a high voltage transformer is there and is a rectified diode bridge with a high energy switching device, and it is controlled by a semiconductor thyristor. It contains three capacitors with a value of 256 microfarad, and these capacitors are connected by parallel, okay, and depend by a power selector cord depending on the power desired. Now these are switched in and out of the circuit by a 15 kilovolt rated spring relays, and we are having some fast power selection ranging, that is 160 joule to 2000 joules. Generally for shallow seismic survey within the territorial waters, we generally use 160 joule. It is more than sufficient for a practical purpose. Now to get the source, that is sparker, which is used as electrical discharges. The electrode, generally this is the sparker with the blue is a blue connector and is a red connector, positive and the negative cathode and the anode. The electric ray models ELC 1200 is used as the sparker source. So it is having a bandwidth of 50 to 4000 hertz. More the bandwidth, more the resolution will be there, the better use. You can see this is a SIG seismic marine ELC 1200. This model is operated with the energies of 150 or 250, 160 to 250 joules, and for carrying out survey to 10 meter to 1000-meter water depth maximum. It is generally we do not go with the ship to such a huge depth. The For shallow geological system, the drift is restricted up to 400 or 500-meter water depths from 50 meter. It emits the 20 decibel of sound signal, that is acoustic signal, that is being reflected from the subsurface layer. So generally, this is the Samsung NF560 global positioning system, which is used for the navigation. This positioning unit is interfaced with the seismic bathymetry data acquisition. Bathymetry means the water depth, measuring of water depth, and seismic we are already talked about. And you can see this is the deployment of the energy source at the sea. We are deploying the sparker, and after that, only after that, the high voltage power source will be switched on after deploying the sparker, and will be giving power to the sparker by the power source, what we have told about in my last slide. So already you have talked about the power source. Now the receiver model. This is a receiver of the streamer of the hydrophone. So generally this SIG, this model from France, is deployed as a sensing or the receiving unit. This is a basic data collection tool in the marine seismic survey. Already the basics about the hydrophone I have, or the geophone I have discussed about in one of my seismic lecture series. You can go through it. So generally talking about it in a very short, we can tell it is provided with a head amplifier, and it is having a wide band with a high output impedance to match the amplifier's impedance. This model acts as a single channel. Why? It is consisting of 20 hydrophones kept in polyurethane tube field, where we'll put aviation and the kerosene oil to get an overall density of the element to 1.04 gram per cc, so that we can keep the streamer below the sea surface swell. That's why this density and material is used. Generally we can have the multi-channel that means not instead of one channel we can have many channels. That also GSI is also doing that survey with a state of art instrument. I'll be talking it about my next lecture or after that, but this lecture only limited to single channel receivers. Now, after the signal is received by the receiver, there is a data acquisition unit. Generally, depth seismic data acquisition unit is being used. You can see that is used for the data acquisition, and is developed by IXSA Blue, and it is dedicated to the data digital acquisition system. It has the provision of incorporating the GPS system, which is synchronized with the trigger number. Trigger number means it is related to the source or the ping, how we are that power source is generating the trigger, that is in synchronized with our GPS. What is this? How it will do the work? It converts the input signal from the streamer cable and the inputs from the energy source and GPS, and it's converted into a conventional SegWi data format, and it saves it in the desired drive location. So it generally the data acquisition units is interfaced with trigger number and the input signal from the streamer cable and from the other input from the energy source. And finally we will get the seismic 2D image. So this is the schematic diagram of the seismic setup, which is used by Onboard Samudra Kaustubh. So this is the power source that I am talking about. The different power energies are selected at 160. These are the two electrodes. So one electrode is just towing at the mark to the water. These two sparker electrodes. There is a common ground is there to earth ground, and what we'll do, we connect the trigger BNC cable, trigger cable, to the CPU, I mean to this of the parallel port, and one from CPU there is a port system, USB to serial port, that is connected with the GPS. So you get it is interfaced with the GPS system to get the navigation information. And how it is powered. So the streamer, there is a three output is there. Output one is connected to the first one analog port of the CPU, and from the streamer is deployed at the deck cable via deck cable to the streamer winch side of the sea. That is the deployment of streamer to the sea, and this is the deployment of sparker or the energy source to the sea, the sparker electrodes. And there is a common GPS system which is connected to all, and it's taking input and giving us the navigation data. So this is how, and this is the GPS, the main connection of the GPS is coming from the wheelhouse of the ship. So this is how our total system works of the shallow seismic instrument. Go to again the same seismic trace model which I have told. There is a source wavelet, or the source is there, and this is a reflector series, and final output is a seismic trace containing the source wavelet along with the reflector series, the output seismic trace. This is the convolution of the acoustic wavelet with the reflectivity sequence. So our main objective is to translate the emitter receiver and to obtain the 2D seismic images formed by the adjacent traces that is arranged in the columns from these traces. When we talk about seismic profile, the parameter resolution is very much important. So when first we will be having in the data domain seismic profile. From data domain, our objective is to convert in the image domain. So there are two parameters, the vertical and the horizontal resolution for high resolution seismic. Generally, vertical resolution is defined by the width of the pulse, or uh, the bandwidth for the modulated emissions equivalently. At When we increase the frequency, the more we increase the frequency, the pulse width can be made smaller. That is, the bandwidth can be made bigger and bigger, which increase the resolution. But in order to increase the resolution, we have to have, I mean, we have to pay the price. And what is the price? This is the decreasing of the penetration depth. So higher the frequency of the source wavelet, the lower will be the penetration depth. For Sparker, the vertical resolution is approximately defined by the wavelet length, that is the lambda by 4. So the more the frequency, the less the lambda. It can be slightly improved by applying the signal processing technique, that is the signature deconvolution. Okay, the penetration. So you can see there is a diffraction is there, so that is being converted to a point source. There is a rho 1 c1, that means the density and the velocity, this layer, and for this layer the reflector there is a rho 2 c2 density and the velocity. This is the penetration depth. Now for pictorial you can see this is the generally will be the representation of a seismic profile of two-way travel time theoretical along the track distance. So this is generally a sea surface, that is a noise above the sea surface. When you remove the water column, that will be removed. These are the reflectors. You can see these are the reflectors, and multiple, that is the, I mean the concept about the multiple has already been described in my previous lecture. Your objective will be to eliminate multiple and keep the primary mm, reflecting events. And this is the bottom, C bottom, and these are the different diffraction patterns which may be converted by single points after the noise elimination technique. This has to be eliminated. Now you can see there's a total 80 millisecond is there, almost penetration. So for 80 millisecond maybe the total recording length that is will be used in the delp acquisition system. So when you convert the two-way travel time 80 millisecond to 40 millisecond, you can get by considering the velocity of the sound 1500 meter per second, we'll get the probing depth of about 60 meter. So with that source we can probe 60 meter below the sea surface level. From this seismic profile we can extract this information. So this is the interpretation panel on the delp seismic. These are the filters description. This is the gain control, and this is the signature deconvolution. So we'll get a typical theoretical seismic section, and in the right panel you can see there are too much multiples are there in the sea surfaces. There the reflector and the multiple. So incorporating the signature deconvolution and the other noise elimination technique which is described in my previous lecture, you can already remove the multiples. You can see that the multiple is very feeble here compared to this. So this will be our objective, keeping the primary reflection very prominent and feebling out the multiples and all other associated noises. So when you apply the bandpass filtering, the filtering at a particular frequency level from 100 to 3000 hertz, because it's a shallow seismic, so there may so bandwidth for Sparker, the bandwidth is I already have mentioned 50 to 3000 hertz. Within that frequency range, you can get a very good process signal by implementing the bandpass signal within a certain frequency range. The raw signal is upwardly, and the down signal is the bandpass filtering. Now there is the interpreted shallow seismic section. One interpreted shallow seismic section of a particular area along east coast, that is Gangapatnam, has been represented. So the reference is our GSI published report, where I am also the author, one of the author, and this is the interpreted seismic section. So you can have a glimpse that there are three reflectors R1, R2, and the R1A. And the geological section, it has already delineated about the beautifully the channels, there's different subsurface reflectors, the different geological events, the truncation phenomena, that is downlap. Acoustic masking means there is a not signal. There is some area where the the ray is not being penetrated, and we need to get proper signal. And there is a signature of fault is also there, geological signature. So we'll have a beautiful seismic section along the east coast of India in this figure. So there is another figure you can get. There is another shallow seismic seismogram, and the reference is being put there, echoed by Geological Survey of India. So there are also reflectors R1, R2, R3, R4. These reflectors are there. It has delineated some reflectors, and the sediment nature is also described. The soft sediments. There is a subsurface faulting nature is there. There is a high amplitude stratified species, means higher acoustic impedance density to velocity. You can see by its high amplitude nature, and that thickness is being shown here by 10 meter. There are different thicknesses. So zone 1 and zone 2 is being marked by this 2. So zone 2 is mainly a uh, soft sedimentary layer, and you can see there is a difference of material is there by this inset figures. And this green is delineating the R2, and this upper one is R1 layer. So this is a particular zooming in a portion. It is also acquired. This is we have taken on the progress report on the geophysical seismic survey. So another, so another, so another picture you can find. There is a I mean, there are seismic, practically acquired seismic sections. So there is a ridges and runnel figure, and the scattered and chaotic seismic signature. There is a valley-like features. This These circles are representing the sample, the points from which we have acquired geological samples, the particular coordinates. There is a soft unconsolidated sediment section. There is a valley with widths and depths is mentioned. The ridge section you can easily see with the height and the width of the ridge is there. And the seafloor and along with the various reflectors, seafloor multiple, along with the C4 multiple that is being faint. So a beautiful seismic section is being presented also of Visakhapatnam, Andhra Pradesh, with the cruise ST286. The reference is there. I think I have you have already get a glimpse of about how the seismic section is generally portrayed, and how it is being carried out, and how to interpret a seismic section, be it a land or in a marine. So hope we'll get the uh, mm, hope you'll get how to tell this. And if please follow my channel, physics and geophysics lecture, and be with